Yeah, okay, so welcome back to this second part of the algorithmic meta-theorem tutorial. So this is where we left. I set up the main question we want to solve, namely finding good characterizations, structural characterizations for classes of graphs which allow and which precisely characterize tractable model checking for first-order logic and monadic second-order logic in particular. So now we start with the upper bounds and the main material. So this is the class of graphs I'm studying for the moment. You see there's a little blue and a red line. And below it is what will eventually turn into something that's called normal dense. And these are sparse classes of graphs. Yeah? And I've used this term a few times without defining what I mean by it. Sparse is not really well defined, but it means the number of edges is sort of linear in the number of vertices. Yeah? Like if you look at a complete graph, then you have n vertices and n square edges, so this is a huge number. And if you have planar graphs, then the number of edges you have is at most 5 times the number of vertices, so this is a very small number, for instance. And so we call something sparse, and just to give you some idea if the number of vertices has a linear connection to the number of edges, roughly. Yeah? But this will be made precise tomorrow morning, what I mean by it. Right, and we start at the very bottom. Okay, there are trees, and we will start here with the most powerful logic and the smallest class we will study. But before we get to precise results, I want to give you some very high-level idea on how we prove these algorithmic meta-theorems, yeah, and some connection between how we actually connect things which we have in the logic to things which we have in the graphs. Yeah. And so this is a graph, yeah, and we want to check a formula in it. And many algorithmic meta-theorems, especially the ones you'll see in the next hour and a half, they are based on one of the following very simple ideas. So we have this graph in a formula, and we don't know what to do with the entire graph. So what we want to do is decompose it into smaller graphs. Yeah? And there will be various notions of decomposition, but everything has in common. We want to make it, we want to cut it apart. Yeah? So we want to split it into 2 separate subproblems and then solve the formulas in the subproblems and combine them somehow and be happy. Yeah? And this will happen all the time, yeah? Except for various notions of decomposition. And a simple type of decomposition is the first one I want to study. This happens when your graph actually, it's a big graph, but it looks like this. So we have 2 subgraphs and they overlap only little. Yeah? There's not a big overlap. So I can sort of decompose them into 2 subgraphs, and then maybe I can do this again. Yeah, and if I find that this subgraph actually has 2 big subgraphs with a small overlap, I can go on. And one particularly nice class of graphs is those which you can completely decompose in this fashion up to the point where these things become constant size. Yeah? And constant size is not we can do whatever you want, yeah, on it. The prime example of this are trees. Yeah, I mean, the tree, you have the root. Once you take it out and you have 2 different subgraphs, at least 2 different subgraphs, they're again trees, so you can recursively decompose them further. And the other type of graphs which have this phenomenon are called bounded treewidth graphs. This is a natural generalization of trees. Yeah? Okay, that's one way of decomposing a graph. Okay? It's like splitting recursively, and this is exactly, of course, what you do if you do dynamic programming or recursive sort of kind of backtracking type algorithm. So you go into smaller subproblems, solve them, and combine. Yeah? In fact, there is a way of making this very formal, which I may mention later on. Yeah? Another way is, I mean, planar graphs, for instance, they don't have this phenomenon so easily. Yeah? If you look at a planar graph, I mean, like it's not clear that you can decompose into 2 subgraphs using only a small overlap. Yeah? It's not possible always. So here for planar graphs, another kind of graphs, we will use a different form of decomposition, because what we can do is we can just try to cover the entire graph by a huge number of subgraphs, but these are sort of smallish or simple or nice. Yeah? For instance, we could try to cover the entire graph by a set of trees of bounded height. It's not clear what this would give us. I mean, of course you can this. Yeah? Take every edge, it's a tree of bounded height. Yeah? But we want a little bit more about these things. Yeah? So we want some control over the overlap of these subgraphs and so on. But if we could get this all under control, then of course we could just say, okay, if it's a tree of bounded height, we can solve for formulas. and then try to combine it using this kind of overlap. This is a lot more complicated, but it works for certain types of graphs, like planar graphs, and actually all the way up to the biggest classes we can get. It's another type of decomposition, more complicated. And this is just two examples, but sort of when you start proving anything about algorithmic meta-theorems, there's always two sides, because you get the graph, and you have a structural property of your graph class, and you get the logic, and we know what to do with logics. Yeah? And if you want to prove such a meta-theorem, then the two things have to somehow match. Yeah? So like we have a logical theorem, which you'll see just in a few slides. It's a Pfefferman-Ward style theorem, which means you can the truth of a formula in a structure can be inferred from the truth of substructures in a precise way. And it turns out that this corresponds in spirit and very precisely also to this proper separation we had in the tree case. Yeah? We can take out a vertex and disconnect your graph into two components. Yeah? And there will be a one-to-one correspondence, and then we can use this one here in connection with this treewidth thing to get good algorithms. Yeah? And in cases where this doesn't work, then there is another theorem you'll see later on, Skyfan's theorem. It's a locality theorem telling you first order logic can't say anything global about your graph. And then you need, if you want to use this theorem, for instance, in logic, you need the corresponding structural property in graphs. Yeah? So you see the locality theorem, it just basically tells you if you want to check a first order formula, you need to check something in local neighborhoods, sort of like two neighborhoods around a vertex. And if you want to use it, then you need a graph theoretical property that allows you to deal with two neighborhoods, to make them easy, to make them nice, and you can use something. And there's another quantifier elimination method, and there's another sort of graph structural property for it. And then finally, we'll combine all of it. Yeah? But the main part of all this research in algorithmic meta-theorems is really to understand the features of your logic. What kind of theorems do you have? How can you rewrite formulas, translate formulas, split formulas into smaller parts, and so on. And what is the corresponding graph theoretical property you can use? And how do you make this all algorithmic? Yeah? This makes it nice, yeah, because you have all these different aspects, but of course you need to put them together in a sense. Okay, let me make this a bit more precise, yeah, so that this makes sense. And because this is more like a logic workshop or summer school, I'll focus on the logical tools we have, yeah, and the graph theory will only be introduced to the part where we need it. But the main goal of the next hour and a half is to present you the main methods that have been used in this research, yeah, the logical methods. Yeah? So what can we do with the formulas to help us doing good algorithms? Yeah? And the first one is the composition method, which is, for those of you who work with automata, they will know this theorem, of course. And it will help us to solve the case on trees. Okay, we need a little bit of definition. The first is the notion of types, first order of types. And let me ask precisely, so who of you has seen the notion of a type? Who knows what the first order type is? And who does not know what a first order type is? And the 90% who know none of the two groups? Ambiguous, yeah, fuzzy types, yes, that's true. Okay. All right. Okay, so here's a type. So we have a graph, and we have a set of vertices in it, and it's a tuple of vertices v1 to vk. Yes, and they're ordered, and they have specific names and so on. And a first order type, and this is the notation I will use for it. Yeah. This one here, the type, and then this is the logic. First order will also be MSO types and so on. Of this tuple in the graph G is just a class of all first order formulas with k free variables, yeah, which are true at these set of vertices k, v. Yeah. So formally, this is the type. It's just a set of all these formulas with variables x1 to xk, which are free. It's first order formula. And this formula is true in the graph G if we interpret x1 by v1 and up to xk by vk. Yeah. And so to determine the type, you just look at all possible formulas in k free variables, interpret by the k vertices you have, and check whether it's true or not. If it's true, it's in the type, and if it's not, it's not. Right? And I'll give an example for this on the next slide. Right? This will not be of any use to us, this concept of types, but it's nice to introduce it anyway. But it's too general in a sense, yeah? Because basically all our model checking algorithms that will come, you take it, you're given a formula, yeah, and you look at some parameter, the quantifier rank of this formula will be the parameter. And then you will just look at the corresponding type, yeah, and you will actually start computing types in your graph. And so this would be an infinite set of formulas, and we can't compute it efficiently. Yeah, so we need to restrict this. Well, it determines the isomorphism type of the substructure. No, not exactly. Well, yes, it does. Yeah, it determines the type. I'll come back to this in 2 slides when we've seen an example. Yeah, then I have something to point. Yeah. Let's first look at the notion we will actually be using, which is a restriction of this. So now we fix the quantifier rank of our formulas. And the quantifier rank is just the maximum nesting depth of any quantifiers in the formula. Yeah? So you look at your formula, and then you look at the syntax tree, as it were, of your formula. And then the maximum number of quantifiers you see on any path from the root to a leaf is the quantifier rank. Yeah? But it doesn't harm if you just replace it by the number of quantifiers for the moment. Yeah? The results will be false, but otherwise it's okay to do it. Yeah? And so for any fixed value q of the quantifier rank, yeah, we can study the first order q type, and it's the same, but it has this little subscript here. And it's just a class of all first order formulas of k free variables of quantifier rank at most q, yeah, which are true at this vertex set. And so this is the type here. You look at all these formulas. If they have quantifier rank at most q, and they are true in your graph when you interpret the first variable by v1 and the last one by vk, and so on. This determines the type. All right, let's look at an example. This is something I just drew in the break, so it's not exactly pretty, but there we go. Let's say we have a colored graph to make the type more interesting. Yeah? So we have the edge relation E, and then we have red and green vertices, and then there are also vertices which are no color class. Yeah? And we want to determine the type, yeah, of U and V. And these are, in case you haven't noticed, this is V and this is U, these 2 vertices. All right, so let's start with quantifier rank Q, 0, sorry. Yeah? What is quantifier rank 0? It means you have no quantifiers at all. Yeah, so. Well, what can we say about these vertices without any quantifiers? So we can say, so we look at formulas phi of x1 and x2, yeah? And x1 corresponds to v, and xy corresponds to u. Yeah? And so to make it easier for us to read, let's just call these variables u and v, yeah? So you know what's corresponding to what. Well, what can you say without quantifiers? Well, you can say v is a red vertex, yeah? And you can say it is not a green vertex. Yeah? And you can say U is a green vertex. And it's not a red vertex. U. Yeah? And you can say there's an edge between them, for instance. Yeah? And that's more or less it. Yeah? And then you have Boolean combinations, of course, of these. Yeah? They're not so interesting because they're actually determined by the atomic predicates. Yeah? So the atomic type, which is how we call types of quantifier rank 0, they just describe precisely the atomic information you can have about these vertices. Yeah? And so one thing that happens here in these formulas, because we have named variables, yeah, which are interpreted by these 2 elements, essentially we have this graph with colors, but now these become constant symbols, so you can speak about them. Yeah? They're fixed constants, U and V, and you know which ones they are. And we want to describe exactly how they look, these 2 vertices. Yeah? And the atomic type just describes entirely what happens with these 2 vertices. Yeah? If there's an edge between them or not, and if they're red or green or nothing. Yeah? And for instance, if you fix this type, yeah, and you take any other pair of vertices like these 2, yeah, and you plug this one here in for U and this one here in for V, if it satisfies the same type, it means they look exactly the same on the quantifier-free level. Yeah? Because the one has to be green, the other one has to be red, and none has 2 colors, and there's an edge between them. It describes basically up to isomorphism the substructure. So if 2 sequences of vertices have the same same quantifier-free type, it means the substructures or the subgraphs they induce are isomorphic to each other. Yeah? And that's the description. And now higher types just tell us how these substructures sit in the rest of the graph. Yeah? Because now if we go on to quantifier rank 1, it means we have one single quantifier we can use. Well, we can say things suddenly like, there is a vertex y. It is connected to V, and it is red. Yeah. Yeah. And there is another vertex y. It's connected to V, and it's green. Because here we have this green neighbor. Here we have a red neighbor, and and we can say there's no black neighbor. Yeah. Sorry, these are all y's actually. Yeah. And so on and so forth. You can start doing the same for V. You say, okay, well, it has a red neighbor, which is V. It does not have any other red neighbor, and it doesn't have any green neighbors and any black neighbors, and so on. Yeah? Sorry?
You have a quality in the language?
Yes. I have everything I want. Yes. Yeah. Yes, I have a quality, especially. Yes, but you only have one quantifier, so at the moment it's not helping so much. Yeah, but
quantifier rank your country quantifier or quantifier depth?
it doesn't really matter for us, but it's quantifier depth. It's a number of quantifiers, but it's the. Okay. No alternation. No. Yeah, you can do it, but it doesn't. Yes, I'm counting quantifiers, but not sort of all of them, just dependent ones. Okay, so here's the definition of quantifier rank. Yeah? So atomic formulas. Okay, I don't want to write it down. Atomic formulas have quantifier rank 0, yeah, because they're not quantifiers. Every quantifier-free formula has quantifier rank 0. And then if you have a formula of quantifier rank k, and you have a quantifier in front of it, it goes up to k plus 1. But if you have a Boolean combination of formulas of quantifier rank at most k, then the corresponding rank will be k as well. Yeah. So for instance, this formula here for all y, rxy, and for all z, rxz, the quantifier rank would be 2. Yeah? Because this is atomic, and then here you have quantifier rank 1, and 1 in front will be 2.
Yeah. I meant it wouldn't really make sense to define quantifier alternation, the alternation rank, because from the moment you've got negation, if you allow yourself, there exists something, and there exists, but if you can throw in a negation, then
you can count it in the definition.
What's that?
You can just add how many, including alternation, to define alternation depth.
I mean, the point is, it's
yeah,
not so
but under
important for us.
negation, you have to be careful, right? Once you allow
You
negation.
can do it, but you have to be careful.
Sure.
Yeah, but alternation is not such an important concept for this, because it doesn't really matter whether it's a universal or eccentric quantifier. It's not like in an automaton where this suddenly makes a difference. What I want is, just counting the number of quantifiers is not such a great measure. It would be okay, but it wouldn't be great because if you go, then we want to be able to translate formulas to whatever we want. Yeah? Like going from one normal form to the next normal form. And it doesn't really matter at all how I define these types. What I want is the properties. For every fixed value of q, then the size, the number of vertices, okay, the number of different formulas of quantifier rank q is finite. Yeah, that's the only property you actually need. Yeah? There are not infinitely many pairwise non-equivalent formulas of the same quantifier rank. Yeah? And then, of course, I want that the union of all q's covers all first-order formulas. So every formula has sort of one quantifier rank. And it doesn't matter at all how you define it, as long as these properties are satisfied. Yeah. But I guess it should be a quantifier rank that's computable in some sense. Yeah, but otherwise, it doesn't really matter. Yeah. And so the main properties are only finitely in the FO formulas of quantifier rank at most q. And this is always up to equivalence. Yeah? Okay, but coming back to this example, so the quantifier rank 1 would just say I have one quantifier and I can describe basically how this vertex V, how it's connected to the rest of the graph, what kind of neighbors it's got and what kind of neighbors it hasn't got. Yeah? And you do the same for green and so on and so forth. And again, you can just show if these two vertices here satisfy the same one type, yeah, then U and V, then they're indistinguishable by first order formulas of quantifier rank at most one. Yeah? And this is the essential property of a type. Yeah? So if you look at a Q type, yeah, and you have a tuple of it that has this type, and any other tuple that has the same type cannot be distinguished by formulas of this quantifier rank. Yeah? And so they're basically equivalent up to every formula we will look at. Yeah? And this is the other property we need for types. Yeah? They're not really describing this up to isomorphism, yeah? Because with one quantifier you can't count how many red neighbors you have. But then we don't care so much about this. Yeah? So any questions on this? Because that would be slightly useful if you had some intuition about what this is. All right. So here's a clean version of this. So we have these full types, which is the MSO type, or we can do the same thing for MSO in any logic actually. Instead of all formulas true at some vertices, and the restricted type up to some quantifier rank, the class of all formulas true at this vertex of this quantifier rank. And like I said, essentially because these formulas all have free variables x1 to xk, and these variables are always interpreted by the same element, v1 to vk, it means we have these elements v1 to vk as constants in our language, basically. So why are we looking at types? Yeah, and the beauty of this is the following theorem, which is they're called Stephan and Ward's theorems because Stephan and Ward prove some version of this, and then everything else goes the same way. And what the theorem says is the following: you have two graphs, G and H. So this is the graph G, and the graph H. Yeah? And the vertices U is the overlap between the intersection of the two graphs. Yeah? All vertices they have in common, in some order, so we can give names to them. And then we can also fix a tuple that lives entirely in G, which is these ones here, and a tuple which sits entirely in the graph H. Yeah? And then the theorem just says if for a fixed quantifier rank Q, if I want to compute the quantifier Q rank type of all these vertices here, so basically the type of these, the union of these three sets in the entire graph, then it suffices if I know how these two tuples, the type of these two in the left-hand side and the type of these two in the right-hand side. Yeah? And furthermore, there's also an algorithm that if you give me these types, then I can compute the new type in the entire graph from it. Yeah? So it's effective, but not very, very efficient. Yeah? Okay, so what does it say? Yeah, I mean, it says what it says, yeah, but what is the main idea? So let's we'll look at two examples, or maybe a quick example. Yeah? Trees, yeah? The one I mentioned before.
Can you say a little more what you mean by G union A?
Well, it's a union of the two graphs. Yeah. No, it's not disjoint. No, it's
just looking at it.
yes, yes, yes. And no, the beauty comes from it when it's not disjoint. Actually, it's also true when they are disjoint. But I mean, these vertices U is just the overlap between the two graphs. Yeah.
So union just means unioning the V and unioning the nodes and unioning the union of the edges.
Yes.
I have a sabotage question.
Yes.
What do you mean by compute?
What do you mean by?
Because you have to represent the types.
Well, I list all the formulas. Well, okay, I know what you mean.
Is there a nice way to answer this question? Is actually what I mean.
Yes, okay. So those of you who know this kind of things, you can follow. The rest just don't listen because it's a technical detail you don't need to worry about. We can sort of normalize formulas. Yeah? So we normalize the way in which you label the variables and the quantifiers, and you normalize the way everything. So you could, if you wanted, even go to Prinix normal form, and then you have a DNF inside. Yeah? And then you just normalize the way in which you represent atomic formulas. Yeah? And of course, in the DNF, you don't repeat any atomic formulas and so on. and in which way you get a sort of descriptive way of listing the formulas by size, if you want. Yeah? And then the type is determined by the set of formulas from this set which are true. Yeah? There will be repetitions and equivalent formulas, and because of undecidability, we don't know how to cut them out, but it will be a finite list of formulas which represents a type. And these you can take as input. Yeah? It doesn't really matter if we have repeated formulas. The only thing is it will still be a finite set. Yeah? But it's a subtle point because it's sort of circumventing the problem that you can't actually determine for two formulas whether they're equivalent or not. Yeah, but this normalization gives you some control. But let's not go into too many details of this sabotage type question. Yeah? But let's come back to this theorem, what it's actually saying on trees. Yeah? So this is the tree, yeah? And I can look at two subtrees. This one here, and this one is the other one. No, that was a poor choice of color. This is a far better choice of color for some very nasty reason. Yeah, and we can just say this is G, yeah? And this is H. Yeah? And so the overlap is just this thing in the middle, that one here, which would be the vertex U. Yeah? So this U here, the root of this trace, which is the overlap between the two subtrees, corresponds to this thing in the middle. And let's say we ignore V and W for the moment. It doesn't matter. Yeah? And then what the theorem just tells me is if I put a constant here, so I put a name to this root, so I know which one it is, and I only look at the red subtree, and I look at the set of formulas up to a certain quantifier rank, which are true at this node in the red subtree, and I look at the set of formulas true at this node on the green subtree, and this information alone, which is a finite piece of information, allows me to determine the set of formulas true in the entire tree. Especially it means I can actually compute them separately, yeah? And I don't need to worry at all about connections between the two. Yeah? And this holds if the overlap is not too big, yeah, because this U has to be constant. So if it's unbounded, of course, then it's hard to say what happens. Yeah? Okay, this is the theorem. I will not prove it, but you can look up proofs if you want. And it's basically, of course, if you know a tree automata what an automaton does. Yeah? I mean, it's assigned a state to the root based on the states it sees on the roots of the subtrees. Yeah? And so it's a finite piece of information. And the same happens here on the logical level. Yeah.
So this could be like MSO formulas or first order formulas.
Yes.
The theorem is for MSO formulas.
It goes for MSO2 formulas, yes. Okay, yeah, everything I say now goes for MSO2. Yeah? But it doesn't work for second order formulas. Because if you have full second order formulas, it means you can just add edges to your tree, and then it will not be a tree anymore, and this decomposition doesn't work. Yeah? And because one of the crucial properties that's implicit in this definition here is there aren't any edges that have one endpoint here and the other endpoint here. No? So every edge lives either in G or it lives in H, which means one endpoint can be in the intersection, but it's not like it can bypass the intersection. Yeah, because otherwise it wouldn't, because it's only the union of G and H. So these edges would not be in G and not be in H. But if you look at this theorem, well, it does actually suggest a model checking algorithm on graphs which can be recursively decomposed into subgraphs of constant size. Yeah, because we start this decomposition procedure, we take the big graph, we decompose it into two parts. We recursively compute the types of the intersection elements on the left-hand side and on the right-hand side, and then just use this procedure here to combine them to get the full type. And so what has it got to do with model checking? Yeah? If I give you a graph in the formula phi, and I ask, is it true in your graph? Yeah? How does it help you at all? What's the connection? Yeah, so how would it help you to know that you can compute types? Yeah? Yes. Because if you look at the formula phi that you get as an input, it will have a fixed quantifier rank. Yeah, let's fix it. Let's call it Q. Yeah? So you set this procedure in motion and you compute the quantifier rank Q type of the root element of your tree. Yeah? And once you've computed it, you can just check whether your formula is actually in this type or not. Yeah? Because if it's true in your tree, if it's true in your graph, it will appear in every quantifier rank Q type. Yeah? Because this formula is it has no free variables, it's a sentence. It just states a property of your graph. And if it's true in your graph, it will be in every type. And if it's not true in your graph, it will be in no type. Yeah? It can't be in a type. Yeah? And so if we know a way of computing quantifier Q types, then we can do model checking. Yeah? It seems very wasteful because you're actually computing truth for all formulas up to this quantifier rank, and then just check the one formula you were given. Yeah, but this is the way it works. Yeah. Is this point clear, or shall I explain a bit more? Because this is the most important part of this. If that's not clear, then it doesn't make any sense. Okay. First of all, you can't read the handwriting, I suppose, but look at this Q equals 1 case. Yeah? And suppose my formula would say, in purple, yeah? The formula I want to verify, it just says there is a vertex X, and it is green, and it is red. I said this, for this pair U and V of vertices, this type for the quantifier rank 1 contains all formulas with 2 free variables which are true at U and V. Yeah? But in particular, it will also contain this formula here where you just say X1 and X2 are free, but they are not being used. And nothing forces you to use these variables. Yeah? So, because this is just a sentence, yeah, it will just be true or false independent on how you choose U and V, because they don't even speak about U and V. Right? Which means if it's true in the graph, it will actually appear in all these types, and if it's not true, it will not appear in any type, yeah, because it's not true. And so, in particular, for sentences up to a certain quantifier rank, there will be in every type as long as they are true. Yeah? And if you have a type, then you can just ignore the free variables and just look at the sentence, and this gives you the answer. Yeah? And now we want to actually use it. You use a theorem to model check on graphs which you can decompose into smaller subgraphs. Yeah? The prime example would be trees.
Yeah. But if all you care about are sentences,
yeah.
Why bother with VW and U here? Why not take them to be the empty tuples?
Because it wouldn't work. Yeah? Because if you use empty, yeah? You see, I'm spoiling my beautiful picture here. I mean, you have to decompose this tree into subtrees. Yeah? But how do you do this if you use empty? You could take this subtree and this subtree, and they have an empty intersection. Yeah? But then it's not easy to combine them, yeah? Because I mean there's an edge between these two vertices, but you don't know which one they are, yeah? Because this edge is lost in the subgraphs. Yes. I mean, if you only look at the green parts, and I'll start with a graph, which is this tree, and I decompose it into subgraphs. And the union of them should actually be my tree, right? And so you can't decompose this tree into 2 disjoint subgraphs without losing any information like this. There is an edge. Yeah? And if you only look at the green stuff,
You only care about sentences, which means you have a lot of choice on how to choose, for example, the arity of your tuples, right?
yeah. But I mean, let's say this is the only red vertex, and this is the only green vertex. Yeah? Okay, I don't need to color it. Yeah. And your sentence could just say there is a red and a green vertex, and they have an edge in common. Yeah? But this is not recoverable from if you only look at the green areas. Yeah? Because, okay, let me just draw it, because this is red, yeah, and that's green. Yeah? And I want to verify the sentence, there is an X, there is a Y, X is red, and Y is green, and there's an edge between them. And if you were only to look at these subgraphs here, in both subgraphs, the sentence is false. Yeah? Because none of the 2 parts has a red and a green vertex which are connected by an edge. Yeah? And so there's no way of recovering suddenly in the entire graph that it's true.
If the theorem proves, will you take U, V, and W to the end?
Yes. But then, but the theorem, if you go back to the theorem, okay, here's a nicer version of it. Yeah? it does say you can compute the type of G union H from these subtypes. Yeah? But if you take here in this example, if you take G union H, it would be the disconnected graph where this edge is missing.
Then something's wrong with the theorem. I mean, you can't have it both ways. The theorem should work. Unless you tell me something about UVW.
It's not always the computer that's wrong. Sometimes it's the user. It's,
because the sentences are in all the types. They don't even require variable. There could be the type of the empty tuple, right? The empty tuple does have a type.
No.
The type of the empty tuple are all the sentences of quantifier rank that are true in the graph, right?
Yes, but look, here's what. Okay, so where do you need this? Okay, we have this graph, which is this tree. Yeah, so I'll draw it a bit quicker. Yeah. And you want to take them disjointly. Yeah? So let's say this is one subgraph and the other one. Yeah? And if they don't overlap, or let's even say you let them overlap.
I understand what you're telling me. I don't see why the
No, I'll tell you now.
theorem.
There is no way to decompose this connected graph as G union H.
No, let's say you decompose it like this. Yeah? This subgraph and this subgraph, but you don't take any free variable. You drop the u. Yeah? Which is, I think, what you're saying. Yeah? Well, why do you need this? But then, of course, you don't know that this is the same vertex in the left-hand side as in the right-hand side. Yeah? Because all you would be seeing in the sub-solutions is this. There's this thing here, and then there's this little blob. Yeah? And this guy looks like this, and this guy looks like this. Right? And you compute whatever you want to compute in information, first-order information here and here. But if you don't know that this vertex is the same as this, right? There's no way of recovering the entire information about the graph.
Stephan, aren't you justifying why a stronger theorem would be false?
No, I'm just trying to motivate why we use this overlap. Because if you're putting sub-solutions together, then it's crucial to know that these two vertices are actually the same in the entire graph. Yeah? Because the truth value would change if you identify this guy and this guy, right? Because it's a different vertex. Yeah? And so even though we only want to check sentences, we need to label the overlap so that we can put these together. Yeah? Yes.
Still, the overlap is only W, right?
It's actually U, because it's the intersection. But you're right, this V and W should actually drop. You don't need this.
Okay. So you only need the overlap. You don't need anything else.
Yeah, in the algorithm you will need this.
For the sentences, you shouldn't need anything other than the overlap.
It's not exactly true. In the technical, it depends on where you apply this. On trees you wouldn't need it. Yeah? But on other structures you will. Yeah? Because let's even say,
completely formal here. You convinced me that you need W to define the decomposition. I'm sorry, not W, V here. What is it? U in the middle, U in the middle. Okay.
Okay, let me give you another. Okay, let me try to explain this as.
No, I'm trying to ask not whether you need them or not. I'm trying to understand why the theorem says that you need more than the overlap.
No, the theorem doesn't say anything. You can just drop them. Yeah? For the theorem, it's for the theorem to be true, you need the overlap U. Yeah, and V and W you don't care. Yeah? But it's just a more powerful theorem, yeah? Because it says you can even label some elements in G and some elements in H, and then your formula can ask specifically: is this vertex with a name A and somehow related to this vertex with a name B? Yeah. It's just like saying I can look at the unit of the graphs and label a constant number of elements by constant symbols.
No, but that's what I say. If your application was only for checking sentences,
yes,
then you don't need the U, V, and W.
No, that's true. But I will need them later on in the algorithm for computing these types. Yeah? And the theorem doesn't care about them. It's just more powerful that you can even have them. But you will need this, what's intuition? Let's say trees, yeah? We have 3 successors, yeah? A theorem tells us how we can combine 2 subgraphs, yeah? And, but recursively, because they're trees, what you want to do is you solve this one, and you solve this one, and you solve this one, Yeah? And it could be necessary, for instance, for this graph minor decompositions. Yeah? These extra constants you can do, they could just tell you which of the subtrees you're going into. Yeah? Because you label the root of the subtree by a constant. And this sometimes is just necessary, that you know which one it is. Yeah? Yeah?
Well, I was going to say, isn't it a simple point that, okay, at the top level you only care about sentences, but when you have a recursive algorithm, subsequently
Yes, but it is a technical detail that you see when you follow the algorithm somehow. I mean, your formula could say something about two vertices of distance 2. Yeah? Distance 2. It could just say, okay, there's a triangle in the graph which is red, and there's a triangle in the graph which is green, and each contains a blue node, and they're connected by a path of length 2. Yeah? And something like this. And then you could find the triangles in all of these subtrees, yeah? But you would need to know, the root of the subtrees you're trying to connect, yeah? Because you're actually saying something about if you have two vertices of distance 2 which are not contained in a single subtree, then it means they have to be the roots of disjoint subtrees, yeah? And in this case, you would actually need to put a label on the two roots you're trying to connect. Otherwise, it's hard to get this information back. Yeah? But it is a subtle point that comes out of the proof. Okay, I want to use this information there to give you some idea on the model checking algorithm, yeah, because this will be the same later on. We have this tree, and I want to use the theorem just to compute types at the root node. Yeah? The idea is actually I want to compute, if this is the root, the type up to some fixed quantifier rank of this in the tree T and the root node R. Yeah? And so how would you do this? Well, you start at the leaves, yeah? And you start at the leaves and you look at this subgraph and this subgraph. Yeah? There are two subgraphs having a common overlap of just one vertex. You compute the type of this edge and you compute the type of this edge. There it's easy because only two vertices, it's not much to do. And then the theorem tells you can actually compute the type of this root in these two subgraphs. Yeah? Which means one application of the Pfefferman-Wald theorem tells you the type of this vertex here in this subgraph. Yeah? And this you do everywhere. So let's say you do this for this subtree, and you do it here and here. No, there's a bit more. And then you combine further, right? You can just take this, and you can take this, and merge them to compute the new type of every node. And so you work your way bottom up through all the entire tree, up to the point where you have to compute the type for every child of the root node. Yeah? And then you apply them one by one, so you merge T1 and T2 using the theorem to get the type of the root plus these two subtrees. And then you apply it again to merge T3 into it, and then you have the complete type of the tree. Yeah? And this is possible bottom up simply by the fact that every tree you can just sort of get by the union of the subtrees plus the root you want to join them.
Can you now say the same story for the sentences of the graph?
What do you mean?
Now you said the properties of the root of the graph. Now I want you to look at sentences. What do you have to do for?
No, I'm not looking at the property of the root. I'm computing the type of the root. Yeah? And the type of the root for quantifier rank Q, in particular, will contain all sentences up to.
The type of the empty tuple now.
Yes.
Tell me the same story now for the type of the empty tuple.
Yeah. I start at these edges, connecting leaf to its parent, and I compute the type of this root node in the. It's the same story. It's literally if you could play back basically. I mean, you have to compute. I am actually computing the type of the root node in the tree, but in particular, this type will contain the set of all sentences of quantifier rank R, Q, which are true in the tree. And then once I've done this, I just throw away everything. I mean, I just look up my one sentence I want to check. But there's no real way, at least I don't know any real way of computing it just for sentences, because for what we just discussed, you merge this information on the subtrees at a common root. Yeah? And it's important that this is the one vertex that's common to both subgraphs. So it has to have a label. Yeah?
No, you need exactly you need just whatever it was. I never U.
Yes.
You only need U. So that's why I say I don't see where formally you need V and W.
You don't need them at trees. Yeah. Okay, tonight I think about a convincing example where you need them on excluded minor class, but it's a bit more complicated what you're saying. Right? But okay, I can tell you a story on sentences. I add a constant symbol to my signature, and I put it on this vertex where you join them, and I just compute sentences. Yeah? And I don't care about free variables. It's cheating, of course, because it's the same as having a free variable, yeah, but that's what you're doing, basically. Yeah? Yeah, I'll think of something tonight. Yeah?
So I'm a bit confused about how you work up bottom up using the theorem. So why is the fact that I know the type of T1 in its subtree and the type of T2 in its subtree?
Thank you for this question. I'm sorry for interrupting, but no, I found this example, yes. Because I think I know what you're going to say. If not, then correct me, yeah? Because how do you do this, actually? So let's look at this sub tree, yeah? This is what you have. And it's got these neighbors, yeah? And I take this one, and I take this one and join them, yeah? And I take this one, and I take this one and join them, yeah? But now how do you go further? Because I don't want to join these at the moment, yeah? What I want to join is, the next step I want to do is this subgraph and this subgraph, right? But for this, what I have as constant symbols is this root, yeah, because it's in my type. I have this root, and I also need to put a label on this root, yeah, because I want to put the label on it because otherwise I can't recover that this is the root. Yeah? And so the next step would be you join this one with this one. Yeah, so you have this configuration. Yeah, and one subgraph you're looking at is this, and this is the other one. And both have this as a label. Yeah? But to continue the entire induction, you also need to put a label here, and this would be your vertex W, which you don't want. Yeah? And if you can't put this extra label on here as a constant, then you will not be able to continue further on. Yeah? And so this is where they come from as well, even on trees. It just somehow maybe it's okay. On trees it might even be definable, but it's not even clear how it would be definable. Yeah. Sorry, I was rudely interrupting your. Okay, very good. Thanks for this question. Anyway, yes. Pfefferman and Ward initially proved this for disjoint unions, and then there's an untraceable and not clear history of extensions of this for this overlap and so on. Janusz claimed that his paper has the first proof of the case where you have a non-zero overlap, Janusz Bukowski. And it's probably true, but then other people tell me, no, this goes back far further, and there's Scheler, of course, has something on it, but yeah, at some point, yes. Yes, and yeah, the disjoint union case is before, but Scheler certainly must have this theorem because otherwise the composition method doesn't work. You see, this is what the style is for, yeah? So that we can just the first, as far as I understand, the first guys who proved a theorem of this type were these two, and then the rest sort of goes along. And I do not want to trace the history through Scheler papers and so on. So just, it's about. I mean, you can prove them in many variations. You can also do the click with thing where you have complete subgraphs. You join two graphs by a complete subgraph and so on. It doesn't make any difference. Yeah. Any further questions on this? Because that's the hardest part of what's to come for the next 10 minutes or so. All right. So then let's go on. Yeah.
This is just for you. Is the connection to Geisman theorem been explored here?
Well, there are different theorems.
I know they're different, but there's somehow they're both telling us something about locality of the logic, right? So I'm just curious whether anybody explored a relationship between them.
I'm sure there must have people doing this, but I don't really see this as a locality theorem, right? Because it works for MSO, for instance. Yeah? So there's something different here because it works for MSO, and we don't have locality theorems for MSO because it's not a local logic. Yeah? And yet we can decompose them here. Yeah, anyone else? On the safe side. I wanted to say, does anybody of you know tree automata? No, that's a good question. No, really, just show some. I will not ask any questions about it. So you're safe to say yes. Okay, so many people know. Yeah? Almost everyone. Because what is a tree automaton? It's a device that has a constant number of states, yeah? And it runs from the bottom to the top. I mean, I know there's variations where you go bottom, top down, but here I'm caring about sort of going up. Yeah? And this automaton just assigns a state to every leaf, and then it goes one up and it assigns a state to this vertex based on the states it sees here and probably the letter labeling this vertex. Yeah? And you could easily take this into automaton. The state of the automaton would just be the set of all possible types. Yeah? And you label just this element here by the type of its of the vertex. Yeah? There's nothing happening. And here as well, which is the state of the automaton. Yeah? And then you label this one by the type of this node in the subtree here. Yeah? So you can construct an automaton from the set of types. Yeah? And conversely, if you have an automaton, it will essentially have a state for every type. Yeah? And you can sort of take this back, I mean, from states to types. Yeah? So it's not two different things. Yeah? Because in both cases, the state of an automaton just captures everything you need to know about a subtree. Yeah? If the automaton labels this by a certain state, this is all the automaton will ever remember about the subtree. So this is the constant piece of information it needs to know about it to decide your tree language. Yeah? And types are nothing else, it's just a different notation for it. All right, so let's go on. So this was for trees, and the way this was describing an algorithm for computing, for model checking, first of all, formulas on trees, so even MSO formulas on trees. Yeah? And the other algorithm would just be you translate it into an automaton, yeah, and then let the automaton run. Both are linear time algorithms. Yeah? Linear time FBT algorithms because the running time depends on the size of the types, which is super big, but then it's only linear in the number of vertices in the tree, yeah? And the automaton is the same thing. And the next, what I wanted to speak about is how we can generalize this from trees to more general structures. Yeah? And the essential piece of information you need, I mean, what makes trees so special is that you have a root, and if you take it out, it decomposes into disjoint subgraphs. Yeah? And you can join them at the single node, which is the root. Yeah? This is what's happening here. Yeah? And a tree is just a graph measure that captures how close a general graph is to being such a tree. Yeah? And so if you look at this graph, you see it's not a tree, but it looks like a tree. And we say it has tree width at most k if you can cover it by subgraphs. So each of these sort of little, the overlap of these subgraphs looks like a tree. So they're arranged like a tree. There are no cycles of the subgraphs. And every subgraph has size at most k plus 1. Yeah? So here it would be just 2, I think, yeah? Because each of these subgraphs only has 3 vertices in it. 1, 2, 3 in each of these patches. And if you take the union of all of them, then this gives you back the entire graph. And if you look at the trees, at the connectivity, also the overlap structure of these subgraphs, this forms a tree. Yeah? And you see this tree here. Yeah? So here, this subgraph, it sits here, and then this one is that one here. And then we have this one as a root, and this another slightly different one, which is this one, and then we have these 2 edges. Yeah? And this is actually all you need to know about tree width if you want. It just says a graph has a tree width at most k if it can be decomposed or covered in exactly this way by constant size subgraphs with k plus 1 vertices. There's a more formal definition to it, but I'm running a little bit late, so maybe I just skip it. Yeah, maybe I just skip it. Yeah. If that is the case, it's unintentional, but what's missing?
There are 3 trees, for example, 3 graphs that contain vertex 5.
Yes, this is true. I mean, they all have this vertex 5 in common, yeah? And yet you can draw them like a tree, yeah? Because, so what do I want by this tree? I mean, I want them to range it like a tree, so we can apply the same argument as for trees, algorithms. And the property I want is every edge in your graph appears in one of these subgraphs. You're not losing any edges if you take the union, and you're not losing any vertices. If you look at exactly what you're saying, if you look at this vertex 5, it sits in here, here, here. So actually all 3 of them have a common intersection. Yeah? But this I can sort of model by just saying, okay, I want these these subgraphs containing the vertex 5, they should also be connected. Yeah? So one comes after the other. So instead of just saying, okay, I'll put them all together in one messy overlap, which is this one, I will split them into a tree. And I just require that the vertex 5, if you look at the subgraphs it's contained in, then this forms a subtree. It's a little bit like replacing a high degree vertex in the graph by a tree of low degree. Yeah? It's just like saying if you have a vertex like this, which has many neighbors, yeah, I want to replace it by a tree which has these neighbors. Yeah? And essentially this gives me back the entire information. Yeah? And this is what you're doing here. Instead of having them all overlap in a complicated fashion, I'll put them in the tree and just say, okay, it has to be decomposed in the tree so that every vertex induces a subtree. And this is all you care about and all you need. Okay, this is made formal in the definition, so now I'm giving you the definition, since you didn't ask. A tree decomposition of a graph is exactly this. It's a tree. Yeah. It can be directed or not. It doesn't have to be rooted at all. And for every node in your tree, you have a set of vertices labeling this node, which is the vertices in your subgraph. And the two properties you want is every edge in your graph for every edge in your graph, there is a node in your tree that contains both endpoints. And if you have a vertex in your graph, and you look at the set of nodes in your tree which contain this vertex, then this is non-empty and connected. Which means you're not losing any edges, you're not losing any vertices, and every vertex forms a connected subtree. And this is a tree decomposition, and the width of this is just the maximum number of elements in such a set minus 1. And the tree width of a graph is the minimum width of any of its tree decompositions. And so this is science because one tree decomposition, every graph has a tree decomposition, you just put everything in a single set. Yeah. So these sets BT are called bags. Throw everything in one bag, then this is a tree decomposition, not an interesting one. And so this just minimizes the tree decomposability of your graph. And the main feature, so here's an example, but I'm not going through, this definition I should mention. A class of graphs is bounded tree width if you find a constant k, so the tree width of every member of your class is at most k. Right? So there's an upper bound. It's like bounded degree graphs, it's bounded tree width and so on. Here's a tree decomposition of a tree. This is a tree. And you decompose it by turning every edge into a bag, yeah, and then you arrange them in the same way as you had it on the tree. And this will satisfy all the definitions and properties of a tree decomposition. So this is a tree decomposition, and the property we have for a tree decomposition, you can prove this if you want. It's not very complicated, but I don't want to do it now. If you look at any tree node, yeah, then this one here, like, it contains the vertices 1, 3, and 11. Yeah, so let's color them. And now let's suppose we delete this. So this one goes, and this one goes. What we have left are two components in our graph. One is this, containing 5, 6, 9, and 10. And one is this, 7, 8, 4, and 2. And these are the two components. And if you look at these vertices where they appear in the tree decomposition, you will find that this component here, all of its vertices are contained in this subtree. And all of these vertices are contained in this subtree. That's always the case. If you delete, for any node in your tree decomposition, if you delete the vertices from your graph, you disconnect it into two parts, which correspond exactly to the subtrees of your tree. Yeah, and so basically it has exactly the same properties as we have for trees, yeah? Except that now, instead of a single vertex at the root, you have at most k vertices at the root. But you can do the same model checking algorithm. You just start at the leaves of a tree decomposition, compute the type of these subgraphs, combine them, and go up. Or you can turn this into an automaton if you want. Yeah? It's the same idea. And if you do this, then you get Courcelle's theorem, which was one of the first sort of explicit algorithmic meta-theorems, which says if you have a class C of bounded tree width, then model checking for monadic second order logic on this class is linear time solvable with a parameterized algorithm. Yeah? So there's an FPT algorithm solving this problem, and the dependence on the size of the graph is linear, and the dependence on your formula is big. Yeah? And the way to prove this is what we just discussed quite briefly. Yeah?
And the favorable theorem was proven for what logic?
Sorry?
The favorable what theorem?
Oh, it goes for MSO. It works for MSO and it works for first order logic.
What about MSO2?
Yeah, that's a subtle point. I mentioned at the beginning that what is MSO2? MSO2 is just monadic second order logic over graphs encoded as incident structures.
So it still should work, right?
Yes.
So it's just monadic second order
Yes.
logic.
The logic hasn't changed because it's actually monadic second order logic, but the encoding is different. And what you can show is the treewidth of a graph is the same as the treewidth of its incidence encoding. Right? Because the incidence encoding just means every edge in the graph gets subdivided once. You put a vertex in the middle and say this is the vertex representing this edge. And the treewidth doesn't change. Yeah? And so this is why you can lift this to MSO2. Yeah. And so now you get this for free. Let's say 3 colorability, you can solve in linear time now on bounded treewidth graphs. And these graphs actually appear in practice quite a bit. It's surprisingly, it's a notion that comes from graph theory. It was discovered before. And it reappears in many, many different areas. So in linguistics, there's a certain notion of things where they have sort of path trees and so on, path graphs. And some of them are nice. And then there's a formalization of what it means to be nice. And this turns out to be treewidth. It sort of reappears at various places. So it's not a very artificial class that has no appearance in practice. Whatever practice really means, because I know nothing about practice, yeah, and I don't even want to know anything about it. So it's, but people tell me who do actually work on this, that these are graphs which you have. It can be made a bit more precise. Like control flow graphs have treewidth 5 or 6, and sort of backbone networks of telecom companies. It's bigger. It's something like between 20 and 40 or so, but it's not huge. I mean, these are American companies with sort of huge number of servers. Yeah, and in theory, so if you could solve these kind of problems now by just coding it into an MSO formula and letting it run. Yeah? And this is 2 nice things. One is for algorithms people, when you look at these papers, many papers, okay, which treat more general class of graphs, they reduce it to a treewidth case and then say, yeah, it's obvious that we can solve it in linear time. Yeah? And there's no algorithm in it, and sometimes it's true, usually, but sometimes it's false. But such a formula would also actually give you a proof that you can solve it in linear time. It's better because it's a one-line proof. It's basically exactly what we've done on trees. Yeah, you compute the tree decomposition, and there's a theorem that you can do it efficiently. And then you start from the bottom computing types, working your way up. Once you know the type up here, then you check whether your formula is in it, and you're done. Let's say we do this procedure, yeah, and we have worked our way up on a huge tree decomposition. So this is super big, yeah, I mean really, really big. Yeah? And I know the type of this node in the subtree. Yeah? Well, there's only constantly many types for a fixed quantifier rank. There's only finitely many of them, which means for every possible type, I could take a minimal tree whose root has this type. I mean, type is just a set of formulas. There's only constantly many of them, so it's a finite object. I pick a tree of minimum number of vertices whose root node has a type in the tree. Yeah? And which means I could just throw everything away here at this point and just plug in a new tree, which is tiny. I mean, tiny, yeah, very tiny, and has the same type. Yeah? And the algorithm wouldn't notice because the Pfeffer-Minwolf theorem just tells us, well, if the type is the same, I can just go on, and I will never see a difference. Yeah? It's the same as saying, okay, I can take for automaton state, I could take a minimum size tree whose root is labeled by this state of the automaton, yeah, and replace it. Which means another way of proving this theorem is you just go up, and as soon as you repeat a type, you just replace it by something smaller. Right? And so you will shrink your entire graph up to the point where it's constant size. Yeah? And this is very easy consequence of this proof, and it's being used sort of in more complicated graph. The algorithms people have noticed this as well, and it's called protrusion reduction, yeah, whatever that really means. Yeah. Which means you can just replace a big part of your graph by something very small, yeah, and then this gives you a size reduction on your graph, and you go on. Side remark, let's first do something else. Okay, this is an FPT algorithm, which means we have a running time. It is f of the size of the formula times the number of vertices. Yeah? And if you want to do it a bit more precise, it is actually fixed parameter tractable in the size of the formula plus the treewidth of your graph, yeah? Times the number of vertices. So you can make the treewidth even the parameter. Yeah? So the natural question is, well, this is very nice, and you can't do better than linear, of course, but what about the parameter dependence? And there's a proof by Frick and Grohr that unless p equals np, there is no such FPT algorithm for MSO model checking, even on trees, where this function f is elementary. Yeah? It means the function f is like a tower of tools, and the height is the size of the formula, the quantifier. And the same goes for even for first order model checking. unless in parameterized complexity, FPT is the same as W1. Yeah? So these functions are astronomical. Yeah? They grow extremely quickly. But this is not the right answer. I mean, for many years, I mean, for decades actually, we've been telling, okay, this is a theoretical result, and it gives us a quick way of checking that something's linear time, but if you really want to implement this, you have to do it yourself and then optimize and so on. But it's actually not true, because then the Aachen group, Peter Rosmanet and his student, Alexander Langer, they just implemented the theorem, and they invented, I mean, they did it a bit more cleverly than just turning it into an automaton. You know? And it turns out it works extremely well. I mean, so he's he's given half an hour talks on his laptop, and he sets this program and to compute the longest path in a 20, 30 node graph. And then at the end of the talk, he's got the answer. You know? So this implementation works surprisingly well. And of course, the other question you can ask, there's a very precise analysis of the parameterized algorithms for dominating set algorithms for bounded treewidth graphs. Yeah? And it's known that you can do this in time 2 to the, so where does the treewidth come in? It's something 2 exponential in the treewidth something, but basically the parameter dependence is 2 to the k log k, where k is the size of the dominating set. And now they ask, okay, if I just put in the formula saying that I want to compute a dominating set on k vertices, and the natural, straightforward first order formula, well, then this implementation they have gives you an algorithm. Yeah? So you can analyze this algorithm and what the time complexity is, and it turns out it's nearly close. It's very close to the optimum. Yeah? So the lower bound you can prove is k log k, something 2 to the k log k, and they get something like 2 to the k log square k. So it's really, really close. Yeah?
So there is a killer app in principle for this, and this is a bounded model checking, in which you get formulas not only of bounded tree widths, but of bounded path widths.
Yeah.
So if these people think they really have something, that's they will have a ready industrial application instead of running SAR, running this algorithm. It's not even that. You don't need to worry about high quantifier alternation because the formulas are fairly simple. I think they are just existential, second order, followed by universal. I think all you need after that is universal first order. It's what called strict monadic NP.
Give it a try. You can download this program. It has a strange name I can never remember. It's called Sequoia. Yeah, so if you Google for it, there are not too many programs by this name. It's by Rosmanet, and the main developer was the student Alexander Langer. And this is from Aachen.
Did I hear you say correctly? You said he gives a talk and he has a graph with 20 or 30 nodes.
Yes.
He's looking for he has a formula that will seek out the longest path.
Yes.
By the end of the talk, the
Yes.
program has figured. So that doesn't sound. I mean, actually sounds like a negative advertisement.
No, not if you look at the argument behind it. Yeah? So they did some analysis. Okay, let's put it a bit more positively. Yeah? So they tested this on one application. They took the Hanover is a city, medium-sized city in Germany, and they took the Hanover urban train, the metro network, and the question was to cover it by Wi-Fi transmitters. Yeah? And so they turned this into the graph, and then they sort of, for every node, when you put their Wi-Fi transmitter, it covers a certain radius, and this radius they turned into a click. Yeah? So it would just be covered, and they compute a minimum size dominating set, and this works. You know? And this is not a super big city. I mean, it wouldn't work with Tokyo, but it's not like a village that has one station. Or so,
And isn't the data dependency okay? So
Yeah,
if you
I
go
mean, I don't
from Hanover
say
to
why
Tokyo-
it should work for Tokyo. It's linear time, right?
Yes, the main problem actually, and this is where 99% of the time is spent, is computing the tree decomposition. Computing the tree decomposition, because that's not so easy, not even in practice. They use some very stupid, not stupid, simple heuristics for doing it, and this generates very suboptimal decompositions very quickly. Yeah? It would be very interesting to check if you sort of give a very big graph and a pre-computed tree decomposition, yeah, because you just know how it was built, how then this would work. Yeah.
The thing is that somewhere the question, how does the tree width appear in the constant part, right?
Oh, this is very much on top.
And that's what's going to kill you, unless you're really dealing with very, very low tree width. The thing that's going to kill you is the tree width appearing somewhere in an exponent. If you have a tree width of it's of 100 and it appears in an exponent, that's it, you're dead, right?
Yeah, well, no, it doesn't, because you're turning this into clicks. Yeah? But I mean, okay, you can check this webpage. I mean, they have these examples in papers where they describe the algorithm. Okay, they did some analysis, and you can download these papers. They compared it to, for several problems, they compared this approach to using CPlex and integer programming. And of course, for many applications, I mean, CPlex was like infinitely faster, but there were some longest paths where they were faster than CPlex. Yeah? And I'm not saying this is what your iPhone has, iPhone 9 will have, yeah? But it's also only a student, I mean, it's like a PhD thesis, right? So it's somebody working out the theory and everything in 3 years. There's no industrial sort of engineering behind.
So this is the longest loop-free path in a graph.
Yeah, which is an NP-complete problem, right?
Which isn't complete, but if you have 30 vertices, you feed it to a SAT solver. I can't believe it would take more than milliseconds.
Yeah, maybe, yes. Yeah, but the point is, like I said, the point is how to compute the tree decomposition. Yeah? And if you have it, then this would be very quick, actually. Yeah? I think. Yeah? It's, but I mean, okay, like I said, I don't want to advertise this as the next industrial tool. Yeah? And what I'm saying is that we have this lower bound of non-elementary parameter dependence. Yeah? But if you implement this more cleverly, then you get something that runs, yeah? And that works optimal for like actual problems. Yeah? Because the real way, if you read these proofs here, what they're really saying is you can encode extremely complicated computational problems very high up in the complexity hierarchy by very, very short formulas.
Yeah, but this is, I mean, the other evidence that the Mona tool, that all of you know, is that even though you have non-elementary complexity, in many practical cases, when you translate from monadic second order to automata, if you do aggressive minimization, and on finite world, for example, there is a canonical logic, you can always minimize, you don't see you don't see a horrible blow up because you don't have this formula that worked very hard to encode very complicated things.
Yes, but this doesn't work. And this you can try, you can kill Mona immediately by these translations. And the main idea that's behind the implementation is you don't want to construct the automaton because it's way too big. Yeah? And so Courcelle has also something on an implementation where he does sort of lazy evaluation of your automaton. So you only generate states which you really need. The trouble with the automaton approach is you actually translate this formula into the automaton without knowing the structure. Yeah? So you're generating states in the automaton for every possible type that some tree could realize. And they get around this problem by just computing sort of bottom-up only the types you need for this one particular. Yes. And this works quite well. And so I think what this shows is there's potential if somebody actually knew how to program and sort of software engineering, you know, with a bit of with a team that would actually do it, yeah, and sort of doesn't come from theory. It could be turned into something that's not completely useless. I mean, completely different from what this result says.
You have to decompose this tree.
I have to what?
Decompose this tree, this graph.
Yes.
This graph, you should offer a true decomposition of it.
Yeah, that's your homework, and it's to find the optimal decomposition. But because it's so, to set a more interesting homework tomorrow, I can show you the entire graph from this graph hierarchy website, and then we start doing this. Okay, so what we've seen now is this case. Yeah, so on tree-like graphs, you can do monadic MSO2 model checking in linear time. Yeah? And you can ask, can we do better? I mean, can we go up? And the answer is fishy, but it's no. Yeah? But it's not very precise, no, and you'll see this tomorrow morning. What I was actually trying to talk about is going up the hierarchy to give you the next central method you need, which is locality-based, which is the locality method for first-order logic. Yeah, so Novi is talking about first-order logic, and the methods I'm going to present will not work for monadic second-order logic. And so here's a bit more of notation. So we have a graph, yeah, and if you know what a Gaussian graph is, then it could be a graph of structure. And the distance in this graph between two vertices, u and v, is just the length of the shortest path. This normal distance you have in graphs. Yeah? And so the R neighborhood of this vertex in the graph is just the set of all vertices in G of distance at most R from your vertex V. Yeah? So normal neighborhood, the closed neighborhood of a vertex would be the one neighborhood, and then you take the two neighborhoods, which are the neighbors of your neighbors, and so on and so forth. And clearly, you can define R neighborhoods by first order formulas. I mean, distance up to a fixed constant R, you can just define a first order logic. Yeah? And if you look at the formula phi with a free variable, yeah, we say that this is R local if for every graph G and every vertex in this graph, whether this formula is true in the graph at this vertex V, which means if you substitute x by this vertex, yeah, then this is true in the graph if and only if this formula is true at this vertex in its R neighborhood. Yeah? And this notation just means it's the induced subgraph of G induced by the set of vertices of distance at most R from V. So if I draw a quick picture, so this is your big graph G, and this is your vertex V, and this is just the set of vertices of distance at most R. Yeah? And then whether your formula phi is true in the entire graph, yeah, depends only on whether it's true in this subgraph. Which means it doesn't say actually anything about the entire graph. It really only speaks about the things local to V. So this is obviously, E is a binary edge predicate and R is just a unary color. Yeah, it's red. And the formula just says x is red is obviously zero local, yeah, because whether it's true or not depends only on x and not, nothing else on the graph. The next formula here that says there's a vertex y which is a neighbor of x, and this one is red. Yeah, so x has a red neighbor. This is one local because whether it's true or not only depends on the one neighborhood of x. I mean, either it's got the neighbor or not. Yeah, you don't need to know anything of distance 2 or more. This formula here that just says there is a red vertex in your graph, it's not local, yeah, because this vertex can be anywhere. It has no relation to your vertex x. Right? So it's completely disconnected. And here's a complicated example of this. So this formula here, it says the following thing. So x is a free variable, which means it's a constant labeling a single vertex in your graph. Just assume this to be a vertex. And it says I have k vertices, x1 to xk, and the distance of these from my labeled vertex x is at most r. So they're all close to this x. And every vertex is either one of these or it has an edge to one of these. This formula is somewhat r local around x. Let me just check this. It could be r plus 1 local, but never mind about sort of tiny changes. Because it says, well, I have k vertices, and they have to be close to x, and then this vertex y can also be, can't be. What is the formula saying? It's just saying, I have k vertices which are close to my x, and every vertex is a neighbor of one of these. Now, if you take a graph, yeah, the diameter of this graph, or the radius of this graph is the most, and this formula would actually say there's a dominating set in your graph of size k, yeah? Because you could just take the center of the graph as x, yeah? And then every vertex has distance at most r from x, yeah? And so it means if the radius of a graph is very small, this formula would be a local formula which determines whether you have a dominating set or not. But if the radius is bigger than r, then this formula is not saying anything, yeah? Because it's not, yeah. It will not determine dominating sets. So why do I care about local sentences? Because of this theorem, which is Greifman's theorem. And this theorem just says every first order sentence is equivalent to a Boolean combination of these things. Yeah? And these things are called basic local sentences. And they have this following syntactical form. You say there are m vertices, x1 to xm. Pairwise, the distance is bigger than 2r for some fixed radius r. But each of them satisfies an r local formula psi. So what does it say that such a formula, if this is a graph? It says I have x1, I have x2, I have xm. They're so far apart that their R neighborhoods are disjoint. Yeah, they will not overlap because the distance is bigger than 2r. Yeah? Within these things, a certain formula psi is true, and it's true. The same formula is true everywhere. And this is a basic local sentence. And the theorem just says, basically, this is what first order logic can do. I mean, every first order formula is equivalent to a Boolean combination of these things. Yeah? And it's a constructive proof. You can actually compute this from a given first order formula. Okay, so, but let's finish this thing about locality so that at least yeah, that's Greifman's theorem. Of course, you can again ask, because before somebody else asked, the question is how big will this formula be? Yeah? So you give me any first order formula, translate it into a Boolean combination of basic local sentences. And how big will it be? It will be extremely big. So you can prove again a non-elementary blow-up. Because they're formulas of size basically k to the 4, it doesn't matter. And as soon as you translate into a Boolean combination of these things, the size will be like 2 to the 2 to the power of 2 is of height k, basically. So it goes up extremely quickly. And again, it's just saying they are very, very short. I mean, very, very concise first-order formulas expressing extremely complicated stuff. For a basic local sentence, now I want a sentence that says there's a dominating set of size k. Yeah? And dominating set of size k does not look like a local property. It's not something you would, I mean, it says something about the entire graph, because every vertex has to be a neighbor in your dominating set. So it's not entirely clear how you would express it as a Boolean combination of these things. Yeah? And you can, and the simpler form is on a connected graph. Yeah? Because what does it mean for a connected graph to have a dominating set of size k? Yeah? So here's your graph. And you're allowed to put k vertices in the dominating set. Yeah? So you put one here and it can dominate 2 of them. But let's say what happens if you have a very long path in your graph, induced path. Yeah? Let's say if the diameter of your graph is big, like this. Well, what can happen? I mean, you need to dominate them all. Let's say it's just a path. So this guy needs to be dominated. The best you can do is put this in a dominating set, which will dominate all of this. The rest needs to be dominated, so you can put this one in, and this one in, and then maybe the last one. Yeah. But if it's just a path, it means every vertex can dominate at most 3 vertices, yeah? Itself and its 2 neighbors on the path. Which means if you have a graph of high diameter, so there's a long induced path, you can't dominate it by k vertices. And so the basic local sentence that's using it is this one. The first one says, I do not have 2 vertices of distance more than 3k, which means if the diameter of your graph is big, then you will have these 2 vertices. Yeah? And if you don't have them, it means the diameter is small. But if the diameter is small, it means the entire graph is contained in the 2k neighborhood of some vertex, yeah? The one in the middle. And so you can just say there is an x, yeah? And then you do something else, which I sort of ignored here. And then you just have to look in its 3k neighborhood, and there you can just use a local formula saying you have a dominating. There's some omissions here, but it's not important what's missing. It's a bit more complicated once you have non-connected graphs. Yeah? And so maybe I stop here with a little exercise for, in case you're interested in these kind of things. Let's say you want a basic local sentence, or combination of basic local sentences saying G has a 2 independent set. Of size k. Yeah, 2 independent means the distance between 2 vertices is 2. Well, let's make it 3 because then it's a bit easier. Yeah? And if you think about this, this will not be very complicated to do. Yeah? But now let's say I give you a graph G and 3 colors, red, green, and blue. Yeah? Or maybe I give you a bit more colors, L of them. And L is bigger than k. And I want an independent set, a 3 independent set where every vertex has a different color. Yeah? So you're not allowed to put 2 vertices of the same color in your independent set. It is first order definable, and hence it's definable by a Boolean combination of basic local sentences. But if you do, it's actually not so easy, and it requires some thinking, unless you know the trick, how it works. Yeah? So nothing else to do tonight, just give it a go. Yeah? And we can discuss tomorrow. Okay, well, thanks very much.